Okay, next up we have Tony, who will be talking to us about aeon. Okay, Coach.
Morning. So thanks, first of all, for inviting me to talk here. My name is Tony Bagnall. I'm Professor of Computer Science at Southampton in the UK. And I've stressed that again, computer science. So I'm here to talk to you, and it's great to talk to statisticians and forecasters, but my area isn't forecasting, or indeed statistics. I did a stats degree in the 90s, so I did a master's stats degree, but since then I did my degree in computer science. I did call myself previously a data miner. Then that doesn't really happen anymore. So now we're all just machine learning, and they're different communities. And it's really useful, I think, to talk to different communities to come here, but you have to be willing to say things that you might think are stupid. So if I say things that are stupid, tell me, because I'm here to learn. So I'm going to talk about Aeon, which is an open source Python toolkit. I'm going to start off by talking about the core developers and the GRE. Aeon is primarily an academic tool with some industry linkage, and it is highly collaborative. I think it's a good example of academic collaboration. The most successful academics I know are highly collaborative. I do not recognize the picture that was painted yesterday of academics being towards that, right? The whole nature of academia is collaboration. And I think we're a good example of it, because we span several countries and groups. So my research group uses Aeon in all its work, right? I make my research group work in a common code framework. They all know what each other are doing, and they all work in interrelated areas. I think it's really helpful for them, especially when we have new people, we're onboarding people, we get them, force them to do everything in a certain way, certain pain in that, but ultimately they understand more what they're doing. So in Southampton, we've got myself, we have Matthew and Chris, who did PhDs with me, and they did postdocs. Matthew's been a postdoc for 3 years, and he's just got a lecturer position, and they're both core developers, and they're both worked in time series machine learning. So that's the UK branch. In France, we have Ali, or Hadi, as we call him. He's in Hotel SAS. He's just finished his PhD with Germain Forestier, who's, excuse my pronunciation, Germain, who's worked with people at Monash as well. He's just finished his PhD, and he's just starting as a lecturer there. So it's another academic, the next generation. Also from France, we have Antoine. Antoine did his PhD in Lorient in time series machine learning. I was an external examiner. I looked at his code. I thought it was really well written. And so I encouraged him to contribute. He then did a postdoc in Paris, and now works in industry and promoting Aeon, signed company. No, I have no idea actually what they do, but sorry, tell you. Spanish branch to David. David is at Cordoba. He was an intern with me. We worked with Romain France. He did some research there. He then did a postdoc, 1 year with me and 1 year in Spain, and now he is a lecturer at Cordoba, right? So this next generation of researchers coming through to make sure that Aeon assists for the future. Sebastian is just in Germany, a German branch. He's finishing his PhD as we speak. He'll probably go into industry. He's not so keen on academia, but that's great. We like to keep links there. He's also a keen advocate of open source. Patrick in Berlin, as well, it's Germany, so he's not a lecturer as yet, but he will be, and he's on track to be, a bit older there, but he's also worked in the field in machine learning for a long time. We have Leo makes another appearance. He's our data scientist, right? So he's a guy who you would understand what he's saying, and he tells us when we're talking nonsense. He works, well, he still works for Halion, but that's sort of changing. But he's the data science guy. And then we have our two latest, Divya and Adja. These were two of our Google Summer of Code interns last summer. They're just finishing their undergraduate, so they're earlier in their career, but they're keen to get involved, and they're finding the way to open source. Okay, so that's who we are. A wide, diverse branch of contributors. What is Aeon's mission? And part of what I'm trying to do is say how we differ from similarly related toolkits, right? But what are we trying to do? Well, I think it's also important when you look at open source is to understand people's motivation, right? Why are we doing it? Because it's often quite hard to understand, right? What's the point of doing it? For me, the reason I got into open source was to make my science, my work, make other people's work reproducible, right? We've all seen the wealth of publications we confronted in that. And there's an awful lot of quite poor quality research in terms of evaluation. In my field, particularly, it's historically been much more emphasis on, is it clever, rather than does it work? So you have a really clever idea, put your 3 pages of maths in, and what I call proof or experiments by anecdote. Here, the data set it works on, it must be brilliant, right? I don't like it. And there's so much research now that you need to be able to differentiate your work from other people. But one way is to repeat experiments that do. We have a common code framework. The idea is someone proposes a new algorithm. They make claims about its quality. Okay, let's port it into Aeon, hopefully by then, sometimes does too, and reproduce our experiments. And if we can reproduce all our experiments, then great, field moves forward. So reproducibility is one thing. We like sitting around coming up with algorithms and clever ways of doing things, right? But ultimately, sometimes what's it all for is the existential moment of the soul is like, why am I coming up with these things and running up on the same problems over and over again? Ultimately, we want people to use our algorithms in real world settings. We want to reduce the barrier to entry from the time someone publishes a paper, the new technique, to someone in a different field being able to use it. So, I speak to people who research in all sorts of fields, like food science, engineers, particularly at the moment, medical people, and they all have their own sort of standard workflow. So, for example, in food science, they always do a certain form of smoothing and use partial least squares. That's what they always do. And why? Because they always have done. Well, that's fine, it's probably good. But to make your science better, having access to a broader range of tools, which you can quickly evaluate your data, your problem on, improves the quality of the science. So we're just trying to make things accessible without what's usually like a 3-year lag time from proposing an algorithm to making it easy for a non-specialist to use. And finally, our third mission is to reduce entry barriers, right? Each of the topics we cover in Aeon represents a huge quantity of research. There's masses of paper. If a new student is coming into the field, it's quite hard to navigate. So by having a standard framework, we make it easier for new people to enter. Okay, that's the mission statement. What's our ethos? Why are we different from other toolkits you may have seen? Well, we're computer scientists, right? We don't use data frames at all. Well, we convert, if you give me a data frame, I'll pull it into an environment. We talked about this a lot when we shifted. We all had the same thing. It seems to me with a data frame, as a computer scientist, that somehow I've got a spreadsheet inside my algorithm. What's that? We work with arrays, and that's our ethos, and that's what we do. And we focus on number. So algorithms implemented with NumPy arrays and number compilation. We're interested in bespoke implementations rather than rapids. Now, I love the whole ecosystem thing. It's great to have an ecosystem, but I'm also an engineer. At heart, I am an engineer, I feel. And it's personal, and I like to see code and how it works. But also, I like to have my code as loosely coupled as possible, right? The more coupled you are with other bits of code, the more errors are going to propagate through your code base, right? So generally, our idea is to implement algorithms ourselves, just the way we are, rather than wrap others. And we don't want everything, right? What we're interested really is some form of state of the art, and that's somewhat subjective, but we will take anyone proposes an algorithm, wants to donate it, and wants to contribute it themselves, that's fine. But if we're going to implement it, we've got to think it's worthwhile. We're not just going to chuck it into the tanker. And we want a broad range of tasks and machine learning. Right. So that's the intro. I want to talk a bit about history, because you know about SK time, right? You know we're a fork SK time. So I'm just going to give you a potted history of how this all developed. Back in 2019, two researchers from UCL in London, Frandce and Marcus, who was his PhD student, approached us and see if they wanted to port our code into Python. Up to that point, we developed exclusively in Java, like Java programmers. In fact, in 2015, the first open source effort we made was a re-implementation of 19 different algorithms and a bake-off paper, which we published in comparison. You know, that was very successful. It was up to 2,000 citations there. And that's what made them aware of us. So, as part of a £50 million system grant to the Alan Turing Institute, the UK Data Science and AI Institute, Frandce and Marcus bid for money, which bought us out. We worked for 9 months. The idea is we're doing the classification side, they're the data science. Right? So that was fine. We did that. I had to learn Python. Didn't like that. Spent a long time swearing at Python and going like, why aren't you really tight and things? Because I'm a Java, C++, C#. That's where I'm from. It is a really very different thing. The toolkit developed. It was led mostly by Marcus as part of his PhD. And we trundled along. Marcus finished his PhD in 2021 and left the project. Right? Now, at this point, we had bid for some money for research. I was kind of thinking, oh, do I want to carry on doing this? I'd already put this grant proposal in. And well, forget the grant proposal. You know, to support SK5 for 3 years, I'm going to have to keep on doing it. Right? But in some ways, I thought the project had run its course, but nevertheless, we did get the fund. So we got 3 years funding for software for research community school. Right? There is money out there sometimes for research software engineering. We were successful. It was at UEA. We appointed, we advertised and interviewed, and Matthew was the best candidate. Matthew had already worked on SK Time, and so he was the postdoc on the grant. This caused some internal arguments, resulted in us leaving. Like, we formed aeon. I'm not going to go into exact details why, if somebody is hurt or whatever, but the point is we had to start again. We were forced to start from scratch, the brand new repository. We forked SK Time. We took most of the people with us, came with us, and then we had to sort out what was going on. So we spent most of 2023 cleaning stuff up. We took the toolkit in a different direction, following the ethos I previously described. We decided, we expanded our base of core developers. We rejoined NumFocus, and we started to explore some outreach. So 2023 was pretty much consolidation year. 2024, we started going out as the world again. We did a tutorial at SIGKDD. There's a link there. We did HTML, and we ran Google Summer of Code projects last year. And all that mapped our advance in functionality. When we started, it was essentially forecasting, all of that side, right, with Marcus and Frandce over there, and classification, our algorithms ported in using number arrays. We sort of trundled along a bit like that. Again, more me swearing Python, convincing Matthew, who's also a Java developer, to port his algorithms into SK Time, which he did. And thankfully he did, because he's a much better programmer than I am. I'm an adequate programmer. I'm a good debugger, I always think, but I'm an adequate programmer. But Matthew's very talented and quickly picked it all up and improved the functionality significantly. Chris brought in a distances module, got a lot of the most comprehensive library, I think, in Python for trying to do his distances. And we've got a very broad clustering module. We went multivariate. Then David, part of his PhD, we did time series regression. I'll talk a bit more about that in a sec. Hadi joined us in 2023, and he's our deep learning guy, right? Which is good. We had some deep learning stuff in there. Mainly, you just poured it in somewhere else from, in fact, his brother's paper but I'm not a deep learning guy. Paddy is our deep learning guy. And that's great, so I don't have to do it. Patrick introduced time series segmentation, again, 2023, expanding our functionality. Sebastian came in with anomaly detection last year, and then Antoine introduced similarity search. And then really what significantly happened was projects I called Kill with Fire. Right? This was basically stripping out the remainder of SD time from aeon. And we just discussed it a lot. I went through the entire forecasting module. It was wrappers, right? We didn't want to have wrappers, so we released that. There were other modules, design decisions we didn't like, operator overloading. I don't approve of it anyway. It was strangely done in escape time. Anyway, we stripped it all out. We reduced the code base from 50,000 lines to 30,000 lines. And for me, that's success, right? I like minimal code. I do not like a lot of code. So reducing the size of it, making significant changes meant we had to have version 1.0, right? First release. And the first release came with our new super lightweight forecasting module, which I promise I will get to talking about in due course. Once I'm going to show you its history. We've got a new module in imbalance because these are 2 new PhD students I've got working in this area. We're running 2 Google Summer of Code projects. We're doing some demos and tutorials at machine learning conferences over the summer. We're going to apply for full membership so that will incorporate to non-focus, whether it takes us or not, hopefully, but that puts us on a more sustainable footing for longer term. And the big news really is that we've got, Paddy and Jamal have got a 2-year postdoc starting in October, the research software engineer who will work full-time on the project. And this is part of the French government's initiative for their AI assets, which is really a scikit-learn super project through Bobble, and then they sub-farm it out to just 3 sub-projects. So, for example, TXLearn, Romain in Rennes has got one as well. And this, again, is going to focus on the deep learning side, if that's their interest, and hopefully will secure the future of aeon for the medium term. Because open source is fragile, right? It's very easy for projects just to peter out. And so we want to keep it going. Our funding will be running out, but we will apply for funding from something I didn't know about, so I moved to Southampton, which is the Software Sustainability Institute. This is a well-funded, long-running project funded by the UK government to promote research software. And basically started in 2012 and invented the concept of research software engineer. Right? That's where that motion started. Now, there are thousands of research software engineers. There's 15 in Southampton, but UCL's at 100. These are departments who are basically helping service open source software 4 times. And they're part of the reproducibility now. Okay, so that's the history, the timeline, and our ethos and who we are. I'm going to talk a bit about the modules and the structure of the code. I'm not talking algorithms here because it's not time or place, but classification is my main field of research, and it has been for the last 15 years. Coming up with algorithms, evaluating them. We've moved into clustering. We have a regression module, which leads us into forecasting. These are classical machine learning tasks, but in the time series context. We also have time series specific tasks, such as anomaly detection. We have a module for that, similarity search and segmentation. Underpinning it all, deep learning as a component, right? We recognize deep learning is important. We haven't got large language models yet, and that far, but we're only doing it as one option. And then we go on to forecast. So that's the task structure. How do we see data? And how do we see that relating to tasks? So in our mind, there's 2 families of estimators. There's one family that works on a single series. Now, it could be a multivariate series. It could have other data as well. But the essence is you have one series, and we model that as a 2D NumPy array. We call it channels. They're the dimensions. That was a long discussion. We call it dimensions. We have channels and we have time points, right? A lot of that's coming possibly from a non-forecasting perspective. But that's what a time series is to us. We're not having any indices, right? So we're not storing time with our data. Mainly because most of the time series I look at is equally spaced. Most algorithms we're looking at do not use time or order. In fact, a lot of the time series we call time series are not even time, right? Some of them are outlines of shapes. Essentially, they're ordered series. Themis in Paris once tried to call it, change the whole subject and the whole topic to data series, but no one knows what that is. So we don't do that. Anyway, that's a time series. We have a base series estimator, and then we have base classes for each of the tasks that are focused on fitting and predicting for single series. We then have collections of time series. Now, this was, again, one of our head-scratching points, and which what you will call panels. I don't know where that name comes from. No one else knows what a panel is. Like, you see, I've got a panel of time series. Oh, what's a panel? We talk about collection. You didn't know what to call them. You were thinking about it, but in an abstract data type, a collection is either a list or a set, right? That's how I teach data structures and algorithms. So we have collections of time sets. We model these as a 3D NumPy array, number of cases, number of channels, number of time points, or if they're not all the same length, a list of 2D numbers. We have a base collection estimator and a base regression, base classification, base cluster. So that's the core functionality. We map between them with transformations. Most of the algorithms we look at are based transforming the time series to get some discriminatory features. You can map a series to a series to a collection, series to a vector. But the idea is you can go from one to the other. So, for example, windowing a single series, we model as a transformation into a collection. We then have helper modules, such as distances, which I already talked about, which we just model as functions, networks, which underpin all the deep learning. So you can have a deep learning classification, which has the same network, there's different final layer to the regression. And we have visualization. So that's basically the core structure we adopt. And the use case is scikit-learn, right? We fit and predict. We load the data to train test data. This is classification. We've got transformations. You can put them in pipelines if you like. You can use scikit-learn pipelines. You can think we even have our own ones. But you just fit and predict, right? That's the essence of what it is. I'm not going to go into it any more than that. What I am going to describe a little bit is the use case, right? Because this, again, I think it demonstrates the reproducibility aspect. I talked about the Bake-Off 2015 paper. We advanced from that. So when we did the 2015 paper, the received wisdom of the best technique was one nearest neighbor with dynamic time. Right? That was mainly due to aeon, who's a friend of mine, but he basically promoted that message. That's the best way to classify time series. It's hard to beat, right? Well, in the 2015 Bake-Off, the best performing algorithm was on average over 112 problems, 6% better, right, in terms of accuracy. In the Redux, the two best performing algorithms, which I won't go into what they are, but they're 12% better, right? And that's on each problem. The average improved accuracy, even and some of them are high, so you can't go much higher. Anyway, that's the first point. So we think that we've helped progress the field and the family of algorithms and the toolkit of algorithms available for classification. The second point is these are from different research groups, right? So HC2 is from mine, but 3 of these are from Jeff Webb's group in Monash. They contributed it, but we helped them contribute them too, right? Because they're very aligned. They'd also worked with our Java toolkit. Proximity forest, PF down there. Each of these is the best in class, right? So there might be 6 or 7 algorithms in that class of algorithms. So this is the best representative. Divya, as a Google Summary of Code, she translated our Java implementation of proximity forest into aeon, right? And then that allows us to evaluate it. Our disk was Antoine's. W2 is in fact right? So it's just showing the utility of having this common framework with lots of people donating algorithms in terms of classification. And this is probably the most mature module in clustering, though, is a more recent approach. As part of Chris's PhD, I get almost used to do exactly the same thing. my research is not particularly emphasizing, right, okay, you've got to do a bake-off. And you look at clustering. Now, clustering is an interesting, time series clustering, an interesting subject. There's much more stats here. The whole body of people in stats who've done a lot of clustering. We're coming at it more, again, from the machine learning side. There were 3 families of clustering algorithms. There's distance-based, which we focused on initially, deep learning, a lot of deep learning clusterers, and there's feature-based. We implement a bunch of them, compare them, comparing clustering algorithms. But that's why I didn't like clustering. Why is one better than another, right? But there are metrics we use. So we'd use some common metrics. We use our label classification data for clustering and measure accuracy, right? It's not perfect, but it's one metric. And then we come up with our own algorithm, again, showing the process of having implemented all these different techniques, we saw ways that could be improved. And Rock the Casbah is under review at the moment, but that's our best approach at clustering. Other collection-based is extrinsic regression. Now we're getting something that regression is something, obviously, you work with more commonly. What is extrinsic regression? Well, essentially, it's a regression problem as we adapt from classification. So we have a collection of time series, and our label is a continuous variable, but it's not part of the series, right? So we're not windowing a series and forming a regression problem. We have an external variable. So, for example, one of the data sets is a pub crawl data set. This is actually in UCI. We've collected it and translated it. So you attach a sensor to people, and then you track their motion through time. And the problem in classification would be to say, are they above the alcohol limit? Right? With regression, it's can I predict your blood alcohol level? So that's our regressor. That's what we're trying to predict. It's extrinsic to the series. The problem I'm working on with a researcher at UEA is virtual reality tracking eye movement, and can you predict the cognitive load of that person based on their pupil dilation? Useful, particularly is medical guys, so they use virtual reality to train surgeons, and if their cognitive load goes very high, their performance goes down, right? So it's useful to be able to predict it, so you can modify the environment. But it's got this strange word extrinsic. This was proposed first by Jeff Webb and his group called Christoph on this paper in 2021. And I reckon they inserted this term extrinsic because it got reviewed by a bunch of forecasting people. So we know what time series regression is. What are you talking about? It's not a new thing. It's got to differentiate. So it has this term extrinsic regression. Chanwei came to UEA, and we worked with a bit of it before this, but they released this archive of 19 problems in 2021. The core finding really was you couldn't actually outperform standard machine learning techniques, right? So you just apply random forests to the data for regression, and it did as well as the other techniques. We worked on expanding this. We expanded to 63 data sets. This was led by David, or David. And we then were interested in, can we convert our classification algorithms to regression? That's the basic research topic. Are the ones that do well at classification, how well they can do regression problems? The simplest one is a convert. We're simple pipelines that are based on unsupervised transformation and then a classifier. You just do the same unsupervised transformation to shove a regression problem in. Now, the two here, Frandce and Dr. Sif, these are both proposed by Matthews, part of his PhD, and they were overall, on average, on these problems, significantly better than all other approaches. And this sort of made me start to think about forecasting. I say, I wonder if we can do time series forecasting regression. Before I talk about forecasting, sorry it takes so long, just one very quick point. Anomaly detection is not my research field. Time series anomaly detection, if clustering is pretty ambiguous, right? What's a cluster? What's an anomaly is even harder. What's an anomaly? If you know what it is, it's not an anomaly. Anyway, there's a whole body of research, and the reason I'm putting these slides up, he did an excellent taxonomy of the different definitions of an anomaly, but they also wrote this comprehensive evaluation and survey, and it is comprehensive, right? These are the algorithms that identify the time series anomaly. Now, it looks like this must be a huge research field. It's not. If you go to Web of Science, time series anomaly, you get about 100 papers a year. that match time series anomaly. Now, time series classification, depending if you need an exact match or not, but up to 3,000 papers a year. Now, for me, that's too many. I can't cope with 3,000 papers in the research field that I work closely in. Forecasting is 30,000. Right? Deep learning is 90,000. Now, this is a massive body of work, right? It's very hard to navigate through all this. Comes back to this idea of having this open source toolkit. But one body of techniques in anomaly detection for time series is based on forecasting, right? You basically fit a model. What all anomaly detections do is they score. So you're going through and score. Score is your error. Get a big error. You're assuming your model is correct. Then you say that's an anomaly. So that's just relating it to forecasting, really. I'm not advocating any of this. I don't know how they do it. Another module we have that touches on forecasting techniques as well, segmentation. So common human activity is a common thing to segment, right? Track motion, are you running, are you sitting, whatever. Again, there's a whole body of forecasting techniques, tar model and things like this are based on fitting separate models to segments. And indeed, a lot of the segmentation techniques are from statistics, right? So we've got a bunch of them. Autoplate was one I had a student implement over the summer based on changes in models. Okay, right, so finally, how am I doing?
Not in 2 minutes.
Oh, come on, starting late. You go on.
No, with the questions.
Okay. Forecasting aeon. So why are we forecasting? Well, firstly, saying you've done regression. There's regression problems in forecasting. I'm interested in having a go at it. But I'm also interested in expanding our extrinsic regression tools. So I've got a PhD student, Alex, started last September. He's interested in doing forecasting. So I think, okay, let's do some forecasting. We've got a team of our core devs who are also interested, which myself, Hattie's interested in everything, to be fair, but he wants to do a bit of forecasting. Matthew, so you're also keen. We've got Leo there to tell us we're wrong, which is great, and we're finding our way through. We have two Google Summer of Code students. Algapal's doing some deep learning implementations. Tina is doing some machine learning implementations, and we're just flailing around going, what the hell is all this? And this is a picture Hattie drew, right? We're a bit Top Gear, like so you can't have a forecasting horizon more than one. Oh, really? And yeah, so we're just having lots of chats like that, finding our way around forecasting. So this is our first go. Now, the whole interface is not set. It's just making up as we go along. We're going to have a base forecaster, which is a series estimator, right? So this is connecting it to the base class that's used for anomaly detection and segmentation. We use a tag system, again, which is still similar to the FK time one, because we kind of liked it, but we have different tags in there. We're having some specific horizon and exogenous tags. We've got a constructor, and we set horizon and constructor. Yeah. One thing one of our Top Gear moments was, there's the forecasting horizon, and there's a prediction horizon. There's different things, right? So what my training model, how far ahead to predict, and how far am I wanting to make predictions for unseen data? They're kind of different things to us. So we have a fit where we're going to pass a series, you're going to build a model, it's our training model, and really strangely, for you, we have a predict where you also pass while. So the idea here, in terms of regression, we're assuming that Y is unseen data, and you don't know what the timing is. Now, with regression, that makes sense, right? You just pass a Y, and we predict on Y. You can do that with some forecasting models. So if I have an AR model, I could run it back and fit it to just any Y, right? You've got a fixed model. In fact, there's a function to do it in stats models. It makes no sense with seasonality because you've divorced yourself from time, right? So this is not the way you might want to do it. Moving average as well. You can't really work on it because you don't know what the errors are. So the idea of predict is not that I'm going to predict for the Y values I pass you. I'm going to predict horizon ahead, right? So think of it as a regression. You pass it your Y values, and you'll say, what's the next one? Now, that's not how most of our forecasting is going to work, because I'm going, what is a forecaster? So for me, from a machine learning perspective, a forecaster is you train on a series and you make a single prediction. Right? I say, learn to train horizon steps ahead, and then do that, right? Now, you may want to predict more than one ahead. You guys probably almost do, but for me, that's a different model. If I want to predict more than one ahead, I'm going to either train the model to predict one ahead, two ahead, three ahead, four ahead. That's what would be natural to me. Or, again, we use the iterative model, i.e. you feed your predictions back in, sometimes called recursive, but it's not recursive, it's a tail recursion of best, so the iterative is better name. Now, this doesn't really fit in BT, so it doesn't fit in particularly well. I have almost finished. We've got a regression forecaster, again, that we have the constructor, we have to pass a window in the constructor, and then it just has, you override fifth. This is overriding the base class in fifth. Again, just code if you want to see it. And this is predict. And we have implementations. Now, I told you I'll make them contribute. Alex has been implementing ETS and auto ETS, ARIMA, auto ARIMA, auto SARIMA. And it's a good exercise to do. I could just use a package, but actually I think it's helped us just to understand how these algorithms work. They're all very much in development. The point is, in regression terms, we can now plug in any regressor. I mean, it's like SD4. So, I mean, it's a similar sort of model, but we can now evaluate all of our regression on these problems. Okay, so I'll just end on there. But I think we have run some experiments, but I'm not presenting results here. This is our roadmap. We're going to develop this functionality. We are open to suggestions, like open to requests. So if there's something that you think is worth putting in. I've got a lot of stats ones. I'm not a monster. I'm not going to make Alex implement them all. But what they are good is for student projects, right? So what I'd like to do with student projects, they say, right, this is the algorithm, implement with aeon, and project, you can evaluate it, compare it to existing, and then we go on from there.
Okay, thank you very much. Please join me in thanking her. We are quite literally eating into morning tea and coffee, so I'll just ask one question and we'll defer the questions out over tea. I had some design differences, I guess, between data frames and your choice of vectors and arrays. Yeah. I was curious how this matches your mental model or your philosophy around modeling by dropping that index. Is it a performance, like a computational decision, or is that a mental model philosophy?
Both, I would say. So I'm basically, as I say, I just don't like data frames. They're unnatural for me. So I feel more is about building a thing that then make predictions or exploring new data. Now, if I'm just doing exploratory analysis, data frame, brilliant, right? But great. You look at stuff, you interact with it. It's interactive mode. I kind of write code in batch mode, and it runs an experiment. And what I don't want to be doing is putting stuff in there in the data frames. I mean, our first efforts were ridiculous. We're like 300 times slower. So we build big ensembles that take attributes in and out, and you find you're passing up and down, and it's just like. Secondly, it is conceptual in that I'm not doing forecasting, right? So most of the algorithms I look at are equally spaced in time, right? Now, you can work out seasonality in order. You can say it needs to be in hours or whatever. But for me, it's just, is it irregular? If it's irregularly spaced in time, then we'll just use a dense model of index. So I guess the conceptual is getting away from notion of time, and I have an index.
Yeah, I'll be the data frame defender, but it does pain me that when there's a regular sequence of time, that we store it in full. So that's something that I'm excited to try and fix and store them as just sequences, starting from the start position, the step size, and the total length, just 3 numbers to represent any regular time events. Do you think that's a computational solution, or I think we might always disagree on philosophy.
For me, if I would store index as a tuple, right? So if I have regularly spaced time rather than have loads of nans, I would store it if I'm going to store it like that. But how I'm going to deal with that is I'm going to pre-process it. Now, if I've got a few gaps, interpolate and make it regular space. If they're irregularly sampled, I'll probably resample it and rescale it, right? So for me, it's kind of a pre-processing. I recognize that's not the universal view, and there's loads of applications, and I'm probably, it's just the way we come up.
Fantastic. Okay, plenty more to discuss over morning tea. So please join me again in thanking Tony.